Good afternoon, everyone. So today our session will be on polymer industry. Um, so polymer industry, it covers most of the polymer is most of the important commodity that we require in everyday life, right? So we will discuss very briefly on the polymer industry in this chapter. So let's start with introduction part. Uh, we know the word polymer that comes from the Greek word that is poly, which means many, and mar, which means the parts, right? So polymer, this word, it means that many parts this has. So there will be many smaller parts which are connected to form polymer. So we will discuss. So a polymer is a large molecule which is a form of repetitive linking smaller molecules, which is called monomer. So polymers generally have very high molecular weight, ranging from 1000 to 10 to the power 7 grams per mole. These are high molecular weight compounds. There are four major industries: plastic, fibers, rubber, paint, and varnish. Those produce and process polymeric material for different end uses. Now, polymers can be naturally occurring also, that we already know, that proteins, polysaccharides, these all are also examples of polymers. Or there can be synthesized polymers also. Now, these synthetic polymers can be classified as either chain growth or addition, and step growth or condensation polymers. We will discuss this part in the later stage. Synthetic polymers, those are the mixture of individual polymers, polymer chain of varying lengths. So, the reported molecular weight of the synthetic polymer will be an average value on the based on the average size of the polymer chain. So, it range around 10 to the power 3 to 10 to the power 7 grams per mole. Now, this is the important part, and the rest of our lecture will be based on this classification mostly. So, what are the bases that we can classify the polymers? First one is uh, physical and chemical properties or structure of the polymer. Based upon that, the polymers are classified into different classification. Second one is mode of preparation. Third one is some physical properties. And fourth one is what will be the technical application of the polymer. Based upon this, the polymers are classified. Okay. So first topic is the polymer classification based upon the functionality or the degree of polymerization, which comes under physicochemical structure of polymers. So, functionality of a monomer, try to understand this functionality. We are talking about a monomer, and its degree of polymerization determines the final polymer that will be formed due to combination of the different monomers. A molecule is called mono, bi, tri, or polyfunctional depending on the number of reactive bonds or reactive groups are there available in the monomer, which are available for coupling at the beginning or during the course of polymeric reactions. So, when we are talking about monofunctional or unifunctional, so it is denoted as U hyphen this functional group U represented as U. So when a single reactive group in the monomer will be there, then it will be calling as then it will be called as monofunctional when there will be a single reactive group. However, a monofunctional group cannot lead to propagation of the polymeric chain reactions. So, uh, okay. So there was an example, right? Suppose you are talking about carboxylic acid. Suppose you are talking about carboxylic acid. So here you can see the carboxylic group. This is only the reactive um, monofunctional reactive group, right? But the thing is, it cannot form itself a polymer. So this monofunctional groups are not that much effective to form a polymeric chain. Second one is bifunctional. When the two reactive groups are present in a monomer molecule. More often than not, the polymerization reaction with the bifunctional groups occur when a double bond that will split to couple with another double bonded monomer. Like n number of, suppose R, it reacts with this. So one double bond will split and it will couple through another double bond. So by this kind of bonding, it forms N R. It forms polymers. It is a chain. Okay. So we already discussed this. These are the functional groups that. Okay. So next one is trifunctional. This is important because you can see when a monomer contains three groups of functional groups, those are reactive in nature. It is important to note that a trifunctional polymer may be a mixture of monofunctional as well as bifunctional monomeric structure. So here you can see one phenol, it reacts with three formaldehyde molecules. Right? When the reactions occurs, it like from this 1, 2 and 3, in these three positions, these formaldehyde groups will react because this formaldehyde molecules, those have three uh, reactive groups in the form of OH group. So H2O will form and those will be attached to these three ends 1, 2 and 3. and it will form this kind of structure. So it is nothing but the reaction of phenol and formaldehyde, phenol and three molecules of formaldehyde, it is forming trimethyl phenol. So this molecule is trimethyl phenol. So here, whatever be the in the formaldehyde, the three reactive groups in the form of OH. So when it reacts with this H, so it will form H2 and these will be attached here. Next basis is basis on the physical structure. So the linear polymers, these polymers have linear kind of structure. Only the bifunctional monomer can form linear polymers. You need to remember that. Only the bifunctional. Monofunctional, they cannot form linear. They cannot participate in the chain reaction. So only the bifunctional monomer can form this simple linear structure. They are generally thermoplastic polymers and they are relatively soluble except for very high molecular weight material. So this kind of we already denoted the bifunctional monomer as B. So this B kind of they will by the chain reaction they will form like that and it will continue. So this kind of linear structure we found in the linear polymer which is found mainly of bifunctional monomers. Next one is the cross-linked polymers. These polymers have 3D network structure type. Only the bifunctional monomers can form cross-linked polymers. Um, elastomeric properties are generally endowed in polymers having cross-linkage across the linear chain. There will be cross-linkage across the linear chain. So the thermosetting polymers have very high thermal resistance, also very high mechanical strength. And those may be formed if the cross-linking among the monomer group is very extensive. So if in the monomeric group, if the cross-linking is high, then there will be high mechanical strength. It is happening for the thermosetting polymer. Like they are bifunctional as well as trifunctional groups are also present as far I remember. Okay, so this kind of structure we can follow that bifunctional groups, some trifunctional groups are there, but this is not like that. It will continue like, but there will be cross-linking among the monomers, like cross-linking with this. So this is a kind of cross-link polymers. So there is the cross-linking. Next one is branched chain polymers. When there is no cross-linking in a polymer molecule, yet the branches arise from the parent polymer chain, then the polymer is called branched. Okay, there are no cross-linking, but still there are some branched which is created on the um, parent polymer chain. So that polymer is ultimately called as branched chain polymer. So small amount of trifunctional impurities in a bifunctional monomer can cause this kind of branching. Branching, which may create several physical properties in a polymer, such as it will decrease the solubility in the solvent, it may rise the softening point, and it may also reduce the thermoplastic properties. So branched chain, okay. So the branched chain polymer looks like bifunctional monomers are there like this. In the parental only, they are forming the branch. It may go on. Then also it is forming branched, and then it is going on like this kind of. In the parental polymeric group, polymeric chain, they are having multiple branched. So this kind of branching, it is uh, how does it impact on the polymers? Those will decrease the solubility in the solvent. Even those will rise the softening point and reduction in the thermoplastic properties. We will quickly look on the schematic of the various physical structure of polymer. So in the left you can see this is linear or chain polymer. So this kind of structure. So here whatever be the structure you are focusing, this is not any kind of chemical bonding. This is the overlaying of two chains. Branched, it means from the main parental there will be some branched. And cross-link means two polymeric, those will be linked like this. You can understand better, right, from this schematic. So next we will discuss the physicochemical structure of polymer based upon the chemical reactions occurring. So, on the basis of the chemical reactions that we are discussing, so depending upon the basis on which the monomers undergo the chemical reactions to form the polymers can be further subdivided. So, based upon in what kind of chemical reactions those are occurring between the monomers, based upon that the formed polymer will be categorized. First one is the type of chemical reactions. First one is the polycondensation reaction. Okay. So in the polycondensation reaction, it is a stepwise process in which the monomers react by eliminating some smaller molecules like eliminating water, NH3, H2O, NaCl. This kind of molecules will be selected and eliminated in the reactions between the two monomers, and those will be in a repetitive manner. So there will be infinite growth of the polymer occurs at the both end, and the condensation reactions terminates when one of the reacting molecules is completely consumed in the reaction. So in general, the bifunctional monomers with different functional groups undergo such reactions. One example that we can give of a condensation reaction is the esterification reaction. Suppose the benzoic acid reacts with ethanol and it undergoes condensation reaction which will give ethyl benzoate, which is a condensation polymer, and eliminating 1 mole of molecule of water. If I want to describe the reaction, so the benzoic acid, it reacts with ethanol. Okay, I will write the this form. It will be easy. So it uh, suppose this is the ethanol. So in the reaction, this will this will be eliminated as a water molecule, and the product you will get ethyl benzoate like OC double bond O C2H5. And water is eliminated. So this is kind of condensation reaction. Next is addition reaction. So in the addition reaction, what happens? These reactions occur by the formation of rapid formation of chains. and there will be no elimination of such kind of smaller molecules. Such reactions generally occur among double or triple bonded molecules or oxo ring molecules. So, addition reaction can further be of three types. First one is the step reaction. So, in the step reaction, the pi bond will be broken and it will form two sigma bonds. Such way, the substrate of an electrophilic addition reaction must have a double bond or triple bond. So, this is a step bond kind of thing. First, pi bond will be broken and two new sigma bonds will be formed in the step reaction. In the second kind of reaction is chain reaction. In the chain addition reactions, the polymer is formed in a single step and within the fraction of seconds. This chain kinetics, we already know it starts with initiation, propagation, transfer, and termination. The third kind of addition reaction, that is ionic reaction, this is very similar to free radical reaction and the reaction initiated with formation of free radicals. But it has positive or negative charges instead of neutral or unpaired reactions. This reaction is very similar to free radical reactions, but here the radicals are not formed. Here positive negative charges they have instead of the unpaired electrons. So I'm not going in very details of each and every reaction. So second topic will be the preparation method. We already discussed what are the physical and chemical structure of polymers. Based upon that, what are the categories of the polymers. Next one, we will discuss preparation method of the polymer. First preparation methods are available, that is condensation polymer. We already discussed that this is a stepwise process. These methods are usually employed for very low molecular weight functional group reactions, where the stoichiometry proportion of the reactions are fixed for the desired final product. During the processing, the solvent addition may or may not be very important for the process. These reactants are usually mixed in a batch reactor with controlled temperature and addition of catalyst. Now, the vacuum processing or azeotropic distillation may be employed to remove the condensation products such as water or other thing to obtain a higher degree of the polymerization in the product. Next category is the method that is available, addition polymerization method. So these addition polymerization methods are carried out with controlled thermal and catalyst conditions, classified into 6 types. First type is bulk polymerization. You can see addition polymerization method. First type is bulk polymerization. What are the characteristics? They result in the purest form and greatest yield of the polymer per unit volume. Also, by the bulk polymerization method, it only involves the monomer molecule, an initiator, and a chain transfer agent. In a large scale batch process, this method is to be run very slowly or in a continuous mode with large surface area for heat transfer, because in the bulk polymerization there is very high rate of the temperature rise. Using continuous bulk polymerization processes, we can have polystyrene and other thermoplastic compounds. Next type is the solution polymerization type, which is also comes under addition polymerization. So there an inert solvent is to be added into the reaction. The solvent enhances the heat capacity, thereby reducing the viscosity and also enhances the heat transfer. Compared to the bulk polymerization process, this method reduces both reactions rate, and molecular weight of the compound. Additionally, batch and continuous processes are used to separate the final polymeric product and to recover and restore the solvent used in the process. Next step is suspension polymerization. In order to control the enormous heat generation that happened in the bulk polymerization condition, the suspension polymerization method was developed to overcome that overheat generation issue. The reaction mass is dispersed as minute droplets of size zero point zero 0.01 to 1 millimeter in diameter in a continuous aqueous phase in the suspension polymerization. But this method cannot be run in a continuous mode since such a system has a very stagnant corners where polymer accumulate may occur. So this we cannot run it continuous. It has to be batch process. This method results in small and uniform polymeric spheres. These are used directly or may be extruded or chopped to form large and molded pellets. Next type is the emulsion polymerization. This is most widely used method of polymerization. This process overcomes the difficulty of heat control and also the low degree of polymerization. It can overcome that difficulties. The organic reaction mass is emulsified with the soap in a continuous aqueous phase and the dispersed particle are smaller in size than the suspension polymerization. It was around 1 millimeter, sorry, zero point zero 0.01 millimeter lowest. So it is less than zero point 0.1 microns, very smaller particle size. The main product of this emulsion polymerization, that is latex, which forms the basis of popular latex paint. Any coagulating and the coagulating the latex with ionic salts and acid, the solid rubber may be found using this latex. The second last one is the homogeneous polymerization. In this method, the feed can be gas, liquid, solid monomers. No initiator required, no additive requires. In homogeneous solution polymerization, the monomer is completely dissolved in the solvent. Whereas heterogeneous polymerization, in the emulsion polymerization, the monomer molecules are emulsified in aqueous media in the form of micelle. For heterogeneous suspension polymerization, the monomer is suspended in an aqueous or other type of media as a large droplet. So now we will discuss on the physical properties of the polymers. Physical properties that includes like order, hardness, density, weathering properties, also includes thermal property, electrical properties like resistivity, dielectric constant, power factor. Other thing like mechanical properties highly covered, that tensile strength, compressive strength, right? Shear strength, impact resistance, and also chemical resistance like chemical solutions, oil, fats, this kind of thing, solvent properties. So these are some physical property of the polymer that covers. Now, based upon the physical properties, the polymers can be classified into thermoplastic, thermosetting, elastomers, and fibers. So, thermoplastic, these polymers are composed of monomers which are linear and have a very moderate branching. They are highly soluble in solvent, but they do not have appreciable thermal resistance properties. Example like vinyl, cellulose derivatives, polythene, polypropylene. Whereas thermosetting, they have very high amount of cross-linked and heavily branched molecules. And these polymers, when they are heated and they will be decomposed, but they cannot be reshaped again. So this is the thermosetting. Once it is heated and it is distorted, it can't be reformed, reshaped to the previous. These polymers have a complex 3D network because it has lot of cross-linked and branched kind of structure. They are generally insoluble in the solvents and very high heat resistance quality. Example is phenol formaldehyde, urea aldehyde, silicones and allyls. Third one is elastomer. These are resistant solids which have considerable flexibility. They are composed of the polymers with glass transition temperature below room temperature. That's why elastomers stay in liquid state, whereas plastics like thermoplastic, setting plastics, so those are in the glassy state. Example of the elastomer, polybutadiene, polyurethane, uh, styrene butadiene, polyisoprene. Fibers, that these are solid forms and forms like thread-like structure, like, and they have very high tensile strength. Example, polyamides, polyester, polyurethane, protein derivatives. So moving forward, we will now discuss on the polymer classification according to the application. Adhesive like application, some polymers can be used for bonding. So these are usually resin type and require some water resistance property. Like cellulose adhesives, vinyls, other cheap natural product like starch, dextrin, protein. These are also used as adhesive. Coating and film purpose. So there a large bulk of polymers are used for manufacturing the coating and films. Free films are polyethylene and cellulosic types, and coating can be manufactured by solvent evaporation method followed by polymerization. For the use of fiber, they are formed by extrusions or spinning of the linear monomer molecules into thin sections of diameter range of 10 to 50 microns, and they have very high good tensile strength like cotton wool. Now we will discuss see the polymer manufacturing process. There are two types of process. One is ethnic polymer process, and another one is the condensation process. So in the ethnic polymer process, polymers are made from monomers having bifunctional groups. Those are called ethnic. Because ethylene has the simplest all form of all hydrogen atom structure. You can see in this structure C double bond C, X, Y, Z, W. Those are representative and simply substitution by other groups or atom. So it will form ethnic. Ethnic kind of polymer process. It includes like polyethylene, polypropylene. So what is the basic chemistry for formation of this? So this is generally n number of this ethylene group. It will form. It will react by simple addition reaction. N number of it will goes on. So this is addition polymerization reaction, and it will have some catalyst in the presence of, so that it forms ethylene, so it forms polyethylene. So what are the methods of production for polyethylene and polypropylene kind of polymers? First method is the high pressure method of this kind of polymer production. So high pressure, it is maintained around 1000 to 2500 atmosphere. So in this process, we are using a catalyst. Catalyst, we use peroxide catalyst, and reaction temperature 100 to 300 degrees Celsius. And the product, it forms low density polymers. Okay. So you can see in this high pressure process, this high purity ethylene and oxygen is mixed, and it is compressed, and it is after preheating, it is sent to the reactor. So high pressure condition 1000 to 2500 atmosphere is present, and from there the product is being taken to the separator. It separates out some of the unreacted ethylene will be sent back to the feed point, and the reacted ethylene, which forms the polyethylene, it will be passed through the chiller to cool down, and then it will be chopped and it will be separated as and stored as polyethylene, right? So the next process, intermediate pressure, where the pressure maintains at 30 to 100 atmosphere. You just remember that it uses catalyst of NO3 or Cr2O3 or alumina catalyst Al2O3, and the products of this intermediate pressure that have high density polymers. And it also increases the tensile strength, softening point, and other things by in decreasing the pressure. You can see in the presence of this kind of catalyst you are getting high density polymers. So quickly look this intermediate process, pressure process, where the metal oxide catalyst are used. So we are getting the monomer which has been compressed, and um, removal of this kind of um, gases will be there. So it is then fed to the absorber, where the solvent is also coming into the absorber, and it is pumped to the reactor, main reactor, where the pressure is maintained 130 to 100 atmosphere. After preheating, it was fed, and some catalyst are fed from the top, and catalyst, metal oxide catalyst are fed. The products are separated out, gas and a solid product, by cyclone separator. So there will be unreacted monomer; those will be recycled back, and the reacted product is then cooled down. Catalyst recovery will be there, and those will be recycled back. The ultimate product of polyethylene kind of thing, those will be filtered, and then it is sent for the solvent fractionator. Alkylate will be separated out. So this kind of intermediate pressure we are getting, mainly we are improving the tensile strength, rigidity, and crystallinity of the polymers. And the last one is low pressure. It is maintained 6 to 10 atmospheres. Um, so in this process also we are preparing high density polymers, and it uses catalyst of uh, aluminum triethyl, activated with heavy material derivatives such as TiCl4. This is the this process is called Ziegler process. So we will discuss this in the process aluminium alkyl. Okay. So this is the process which is famous Ziegler process, low pressure process for polyethylene production. We will discuss that aluminum alkyl and TiCl4 or TiCl3 is fed both, and this is the catalyst preparation stage. From that the catalyst slurry is fed to the reactor, also ethylene. After some treatment like sulfur compound elimination and oxygen H2O, this kind of elimination, it is fed to the reactor. From the reactor, the product is sent for the flash drum. The from the gas, it is like mostly the catalyst is separated, and those are dried and recycled to the catalyst preparation process, and the polymerization product will be sent through the filter, Wet polymer is being dried and then we are getting polyethylene. And water, whatever is that, it will be sent for the makeup water or retreated water. So this is the Ziegler process because yeah, just you have to note down that reactor temperature maintains at 70 degrees Celsius at 7 atmospheric gauge pressure around, and flash run to separate the catalyst that I already discussed. So here the product is being polyethylene. Same process, same low pressure Ziegler process can also be used for polypropylene production as well, right? Okay, so now we will move on to our next process, that is ethnic polymer process manufacturing of polyvinyl chloride or PVC and its copolymers. So the basic chemistry involved in this process, that is addition kind of kinetics to produce these linear polymers. Like when you talk about PVC, so vinyl chloride we will have, and n number of this vinyl chloride will react in addition kind of reaction, and it will form polymeric reaction. It will form polymers, so it will form polyvinyl chloride, PVC. And other this kind of, suppose n number of this vinyl chloride will act with n number of CH, n number of CH2CH, this other kind of reactions, so it will form this kind of Cl, and here X other uh, group, and it will be M plus N. So M is generally greater than the N, and here the X group is nothing but comonomers. Examples: COOH, OH, carboxy ester. This kind of group is comonomer, so it will attach here. Okay. Now let us focus on the method of production for PVC. So this is the reactor, and it is continuous polymerization reactor, where we are giving feed of water, catalyst, detergent or soap molecules, and vinyl monomers. Okay. So after the reaction happened of polymerization reaction, some of the monomers, unreacted monomers, will be separated by the flash drum, and it will be recycled back to the feed point. And the polymerized product will be taken to the coagulation tank, where acid is being given to coagulate um, uh, one thing that you can say, that from the uh, okay, let us describe more specifically. The water that gives like 100 parts of water, 100 parts of vinyl monomers, and in the catalyst, and 1.5 parts of detergents. It is fed to the pressurized reactor for 50 degrees Celsius, and 72 hours it is fed. So this is kind of emulsion and suspension polymerization method. So the micellar polymer particles can be further stabilized by addition of more emulsifying agent. in the coagulation process, and such as vinyl latex it also added. If the solid polymer is required, then the mixture is either acid coagulated and dried through the spray dryer to form the solids. Next one, the type is polycondensation process. So polycondensation process is defined as a stepwise reaction, right, of monomers with the functional group, which often eliminates small molecules like water. These can be both linear and tridimensional polymers are made. Later on is more prevalent. First one we will discuss about phenol formaldehyde resins. So here um, the basic chemistry involves that the methyl monomer formation is occurring. So phenol it acts with X number of CH2O and it forms this kind of structure. In the next, it is forms the linear polymerization. So in the next step, m number of this group, this m number of this what I can say, m number of this product participates to form the chain kind of structure. Substitution here of the non-functional group in the fourth position. This this position will block the cross-linking possibilities. And cross-linked of the tri-dimensional polymer of this cross-linking, it will all form like this. Okay, so this will. So we will now discuss about the phenol formaldehyde resin preparation. So here the solvents, phenol, formaldehyde, catalyst and modifiers are all sent to the batch type of reactor, where the cooling jacket is very important because polymerization reaction is a exothermic process. Now the reaction starts and the reaction of heat of reaction is removed by this water cooling jacket. So in the earlier stage of the reaction, the heavier viscous resin separated as a bottom layer and aqueous will be in the top layer. So in the next step, it is dehydrated by the combination of the heat and the vacuum. Now the fused resin at 130 to 150 degrees Celsius is removed from the kettle and then it is cooled and ground to fine powder. 200 mate it is ground and uh, it is then sent through the resin storage. Some filler plasticizers are added for more modifying of the polymer, and then we are having thermostatic molding powder. So these are some pre-processing. Main polymerization reaction is occurring inside the reactor and the fused resin is taken out, and this is uh, in the solvents, resin in the solvents, this is producing laminating resin or coatings. Resins in the water solution, it is producing adhesive or coating, and some of the molten resin is taken, water cooled and then meshed it up, and then it is mixed with filler and plasticizer, again heated, dried, and then it is formed molded powder form. So the next part is the epoxy polymers. So epoxy polymers, say this is the mm, first step is the epoxidation, where an addition of the oxygen atom is occurring at the C double bond C bond. Okay, so so C double bond C bond, it acts with oxygen. So one atom only. So it will form this structure. So oxygen transfer agent can be any form. Not I should not write oxygen. So there should be some transfer of um, oxygen transferring agent should be there. I should write like this oxygen. It can be of hydrogen peroxide or chlorhydrin. So later gives the epichlorohydrin, like when it reacts with, it forms allyl chloride, and in the presence of the this it forms some intermediate product of this, from where the HCl will be removed and it will form the epichlorohydrin. So this is the process. Another one we can discuss, that is the suppose epoxide polymer that contains a epoxy group at the end of the polymer. uh, it may be like epichlorine reaction with bisphenol A. By these reactions also we will get a epoxide polymer. So what kind of reaction it involves? So it forms the epoxy resin, that is quite a big structure that I am going to write. And here this group is Okay, in between there will be CH3. This is a very long structure, and in number of this is a very long structure. I'm sorry that I couldn't accommodate in a single line. So this is the kind of epoxy resin. Another kind of this epoxy monomer can also obtain from the unsaturated natural products such as vegetable oil, particularly soybean oil and others. Molecular structure of the polymers from the epoxide natural product monomer is extremely complex. And if we talk about synthetic epoxy monomers, those are obtained by via butadiene cyclization and peroxidation. That is synthetic epoxy monomers. Those are formed by this kind of reactions. This is vinyl cyclohexane. It reacts with hydrogen peroxide, and it forms the synthetic epoxy monomers, right? Last one we will discuss about polyurethanes. So it is also a condensation polymer, and it is shown that the reaction of the dye and polyisocyanate with dye and polyols form the polyurethanes um, with different uses, right? Polyols are used as a main raw material along with methylene diphenyl diisocyanate or toluene diisocyanate are there in manufacturing of the polyurethane foams. So, what is the manufacturing process of polyurethane is involved? Thermoplastic polyurethane are formed by linking three basic components which are mentioned below. Number one is a linear hydroxyl terminated polyol with molecular weight of 500 to 3500. A diisocyanate which may be aromatic such as MDI, TDI and other things. However, MDI is preferred in general, and a low molecular weight glycol such as this 1,4 bu- 1,4 butanol and ethylene glycol 1,4 phenyl b hydroxyl ethyl ether. These are used to serve as a chain extender. So this is how the polyurethane is formed. So that's all for today's class for the polymer industry. So we almost covered most of part of the polymer industry, not in so much of details, but we have touched upon all the category and mostly the classifications of the polymer that we can do. And in the next class, we will be discussing our last chapter of this course. Um, in the coming week. So if there is any question regarding the rest, regarding all of the classes that I have covered based upon the syllabus, you can ask question in the NPTEL question and answer that platform. And even if you have any question, you can also comment on my YouTube video so that I can refer to this question in the next class, which will be the last class from my side. Uh, Thank you for today's class. I'll be signing off now. We will meet in the next class next week. Thank you.